Welcome dear students, we are on the CC Gurukul lecture and we are in the series of the quantum technology and we are discussing the quantum devices and we are discussing the squid. Now we discuss some of the application of the squid. Squid having a various application at this as this squid measure the sensitive or measure the very small magnetic flux easily. So squid device are majorly used to identify very small amount of the magnetic field. So current, voltage, inductance and the magnetic susceptibility. These are the application of the squid. So these devices show excellent sensitivity in the magnetic flux detection. So the devices have been used to detect the small magnetic flux or the small quantity or small value of the various parameters. So these devices are used in the form of magnetometers and gradiometer. Various area of the squid devices are as follows. Number one, it is the if we just measure the weak magnetic field which is produced in the brain by presence of the electrical current occurring naturally in the brain. So this squid magnetometer are used to measure the magnetic field and thus perform the brain activity mapping. This technique is known as the magnetoencephalography, that is the MEG. Another technique which squid devices are used to record the magnetic field produced due to the electrical activity from the stomach, that will also be measured through the magnetogastography. Another squid sensor which are used to detect the dosage form of an orally applied during through the instantial tract containing a little amount of the magnetic, that is Fe3O4, which is a magnetite and is magnetized by the high energy magnetic field, which is a magnetic marker monitoring, that is MMM. Another measurement of the magnetic properties of the system is the fundamental commercial use of the squid sensor as the magnetic property measurement system. Apart from this, the technique which is having a simple, which is placed in the center of the squid detection coils by applying the external field or RF excitation to the sample, corresponding signal are measured is the super paramagnetic relaxometry, SPMRM, that is NMR and EPR. By moving a squid sensor across, examine the area of weak magnetic field which is measured through the scanning squid microscope. In the technique, squid magnetometer are used to detect the infinite deviation in the Earth's magnetic field. The techniques is most commonly used by the military forces to detect the submarines is the magnetic anomaly detector, that is MAT. Now what are the limitations of the squid technology? Since the voltage output of the squid loop is a periodic function of the flux, thus the squid sensors are susceptible only to the since the voltage output of a squid loop is a periodic function of the flux, thus the squid sensors are susceptible only to the relative changes of the magnetic field and the current. So the operating point of the squid sensors can shift by one or more magnetic quantas. If the corresponding electronics of the feedback does not follow appropriately to the signal changes, that will change the total signal, that will be the half of the magnetic flux that will be applied. So the maximum bandwidth of the squid is approximately half the biased frequency due to the use of AC biasing, which generates the 1/f noise in the sensor. Now, up to now we have discussed the squid. Now we will discuss the another quantum device. Squid used for the measurement of the magnetic field, voltage and the magnetic susceptibility, which is in the very less amount, less parameters we can find out by using the squid. Now the another device we will discuss, which is the quantum cascade laser. This is the device which is used, the normal laser we use, but in the quantum we use a quantum cascade laser. There is a light emitting device, that is also LED light type, and junction laser we use here, that is also called VCSEL. So what is this QCL? This QCL is the quantum cascade lasers. These are the semiconductor lasers. Semiconductor laser we have discussed in the previous lecture. Now the cascade lasers, that is a quantum cascade laser, is also a semiconductor laser that emit in the mid and the long wave IR band and are finding the new application in the precision sensing, spectroscopy, medical and the military application. Their wide tuning range and the fast response time allows for the faster and more precise compact trace element detectors and the gas analyzers that are replaced slower and larger FDR. Mass spectroscopy and the photothermal microspectroscopy system. So this tuning range and the fast response laser allows to just get the precise and compact tracing of the element detection gas analyzer compared to the other spectroscopic devices. Since the first operational QCL emitted light in 1994, tremendous efforts has been put into making them more robust, versatile and the manufacturable. So quantum cascade laser are used in the industrial exhaust sensing, safe distance explosive detectors, light sources for infrared imaging system, medical diagnostic, breath analyzers and a variety of other sensing and spectroscopic applications. So number of market of QCL is growing at an ever increasing rate as scientists and manufacturers gain more experience with them. So a quantum cascade laser is a special kind of semiconductor laser, usually emitting the light in the mid-infrared or terahertz radiation, in contrast to the ordinary laser diode, which rely on the electron hole recombination between the different electronic bands, that is the interband transitions. The laser diodes which relies on the electron hole recombination, that is the interband transition. A quantum cascade laser is a unipolar device. It uses only the electrons and operates on the inter subbands transitions. The laser diode use the interband transition, but this quantum cascade laser use the inter subband transitions within the conduction band of the tailored semiconductor heterostructures. The gain medium consists of a large number of the gain medium, as we use the gain in the laser system. So the gain medium consists of a large number, typically the several tens of the repeated periods of the quantum well and the barrier grown with the precise control layer thicknesses. Each period can be divided conceptually into the two parts. This is for the quantum cascade laser. So the gain medium consists of a large number of repeated periods of the quantum well and the barrier. We are having a various quantum wells in this cascade laser as well as a barrier, and with a particular boundary condition which grown precisely control layer thicknesses, and each period can be divided conceptually into the two parts. First is the active region, second is the injector region. In the active region, one or more quantum wells where the upper and lower laser levels are formed. We are having the two layers, the upper layer and the lower level will be in the active region, while the injector region is sequence of the wells and the barriers engineered so that electrons are efficiently transferred from the lower level of the one period into the upper level of the next period, that we will discuss. We will see through the diagram. Now, in the laser we are having a upper layer and the lower layer, that is active region. The injector region where we are having a sequence of the wells and barriers, and now the electrons are efficiently transferred from the lower level of the one period where we are having a high population inversion into the upper level of the next periodic layer. That will be the injector region. Now, the QCLs operates in a fundamentally different way than the diode laser. Now, how it is different from the diode laser? As the diode laser depend on the process of electron hole combination, as electrons from the conduction band recombined with the holes in the valence band, and in the process is the single photon is emitted. Diode lasers are limited to about 2.5 micrometer wavelength because the wavelength is determined by the recombination energy or the band gap of the material system used to fabricate the devices. Different materials combinations result in the different band gaps, but there is a limit to the materials that can be used to make a diode laser. So, now through diagram we will illustrate the QCL operation. Now, you see here there are a various quantum well, and you can see we are defining the two region. One is the active region, second is the photon. There is another reason is a photon emission. Means here we are having the one region where upper region and lower region where the there is a transition takes place, and one is the transfer the population to the other level. So, quantum cascade laser energy band defined by this manner: active region and the photon emission. Now, you see there are various potential wells with the barrier. Now, QCL are unipolar, and laser emission is achieved through the use of inter-sub-band transition in a repeated stack of semiconductor multiple quantum well heterostructures. An idea first proposed in the article where it is defined the possibility of the amplification of the electromagnetic waves in the semiconductor with a sublattice. Means here we are using the sublattice, and in this sublattice there is a intersub-band, and there is a transition in the intersub-band by achieving the emission and use of repeated stack of a semiconductor in the multiple well heterostructure. So, intersub-band and intersub-band and interband transition, how they are different. Interband transition in conventional semiconductor laser emit a single photon. Within a bulk semiconductor crystal, electrons may occupy the state in one of the two continuous energy bands. So, the valence band which is a valence band, which is heavily populated with the low energy electrons, and the conduction band, which is populated with the high energy electrons. So, two energy bands are separated by a energy band gap, in which there are no permitted states available for the electrons to occupy. Means we are having a conduction and we are having a valence, and there is no another band between that. Conventional semiconductor laser diode generates the light by a single photon being emitted when a high energy electrons in the conduction band recombines with the holes in the valence band. Then there is a spark will come out. So, the energy of the photon and hence the emission wavelength of the laser diode is therefore determined by the band gap of the material used. But in QCL, however, does not use the bulk semiconductor material in its optically active region. Instead, it consists of a periodic series of thin layers of varying material compositions forming a super lattice, because we require the super lattice and we require the subbands. So, it is not using the bulk material, it is consist of a periodic series of thin layers of varying material composition forming a super lattice. So, the super lattice introduces a varying electric potential across the length of the device. A particular boundary condition we will use for this, and the potential we are having a across the length of the device will be the same, measuring that there is the varying probability of the electron occupying the different position over the length of the devices. So, this is referred to as the multiple quantum well confinement and lead to the splitting of the band of permitted energies into a number of discrete electronic subbands. As we have seen that there is a potential well and all are having the discrete electronic subband. Or we can say we are having a number of discrete electronic subband. Now, by suitable design of the layer thickness, it is possible to engineer a population inversion between the two subband in the system which is required in order to achieve the laser emission. The basic requirement of the lasing action is the population inversion. So, to achieve the population inversion between the two subband in the system, there is a requirement of the laser emission. So, because the position of the energy band in the system is primarily determined by the layer thickness and not the material, it is possible to tune the emission wavelength of QCL over a wide range in the same material system by layering different material or by layering the various thickness of the material. Now, you can see on the screen that this is a conventional where the conduction band and the valence band, we can say this is the interband transition. In the conventional semiconductor lasers emit a single photon and that produce a lasing light. Now, additionally in the semiconductor laser diode, electrons and holes are annihilated after recombining across the band gap and can play a further part of the photon generation. However, in the unipolar QCL, once an electrons has undergoes an inter subband transition and emitted a photon in one period of the sublattice, it can tune into the next period of the structure where the another photon can be emitted. This process of the single electron causing the emission of the multiple photons as it transverses through the QCL structure give rise to the cascade, and cascade, the name as the name suggests by the cascade, and make a quantum efficiency of a greater than unity possible, which leads to the higher output power than the conventional semiconductor laser diode. Why it is a cascade? Because we are not having a single, but we are having a multiple photons as a transverse through the QCL structure. So, a cascade we will get, and that makes it the more efficient. Now, we can see this, we can understand by this diagram. Now, you can see easily that there is a periodic potential well, and you are saying that that is the electron that is come out in the cascade manner, H nu or H omega, anyone H cut omega you can have here. So, in quantum cascade structure, electrons undergo the inter subband transition and photons are emitted with all the subbands. Now, the electrons tunnel to the next period of the structure and the process repeat. Now, this energy will go to the another period, and then the process will continuously repeated. So, QCL are typically based upon the 3-level system, assuming the formation of the wave function is a faster process compared to the scattering between the states. The time independent solution to the Schrodinger equation may be applied here, and the system can be modeled using the rate equation. So, quantum cascade lasers are comprises of dozens of alternating layers of the semiconductor materials in the form of potential well that forms the energy quantum energy wells that confines the electrons to the particular energy state and produce the light in the form of the cascade. So, as each electron transfers the lasing medium, it transitions from one quantum well to the next, derived by the voltage applied across the devices at precisely engineered locations called the active region. The electron transition from one conduction band energy state to the lower one, and in the process emits a photon. So, electron continuously through the structure, and when it encounters the next active region, it transitions again and emit the another photon. So, in this manner each quantum well produces a photon. So, multiple photons we will get. So, this stimulated emission is also known as the inter subband transition occurring within the conduction band. Yeah, it is in the conduction band. So, we are not using the conduction band like in the semiconductor, but in the conduction band there is a inter subband transition. So, the QCL may have as many as hundreds of the active region, and each electron generates that many photons as it transfers the structure. So, output wavelength is determined by the structure of the layers rather than the lasing material, and that means device fabricators can tailor the wavelength in the way that cannot be achieved with the diode laser by changing the material of the layered material. While the diode laser output wavelength is limited to approximately 2.5 micrometer, QCL operates at much longer wavelength, mid-wave infrared protection devices up to the 11 micrometer and available up to the 25 micrometer emitted have been made on the experimental basis. So, this transition range is useful because of the large number of the absorption line exhibited by common target gases that fall within this band. So, terahertz QCL are now being commercialized, and some emitted as a range of 100 micrometer to the 150 micrometer. More complex gas molecule absorbed at the longer wavelength, and the greater measurement accuracy is possible with the QCL based system than with the current technologies. So, QCL allows for remote sensing of complex molecules, whereas most traditional methods require a sample of the subject material. Some technical changes remains before these systems are commercially viable on the large scale, but the technology is advancing. Now, through this diagram, we can see how the energy is transferred from one part to the another. Strongly simplified schematic diagram for the gain region of the quantum cascade laser. Here we are having a 3 color of light. One is blue, second is the 3 arrow, one is the blue, second is the red, and third is the gray arrow. So the diagram shows the electron energy versus position in the structure which contains the 3 quantum wells. Now there is a 3 quantum wells, how the energy can be transferred from one to the another. So the overall downward trends of the energy towards the right hand side is caused by the applied electric field in the reality, and each gain region must be divided into an active region and the injector. Now you see now how this the energy, the gain region in each period of the structure, this following happen. First step is that the electrons is ejected into the upper sublevel, that is the mini band in the active region, and undergoes a radiative transition to the lower subband. This is the lower subband, upper band and the lower subband, that is represented by the blue arrow, to the lower sublevel, and this is the laser transition on which stimulated emission occur. Now we talk about the red arrow. Now if then relax by the fast non-radiative transition, that is through the red arrow, typically via the photon emission to the lowest sublevel of the ground, means all the electrons will come at the ground level. Now the third step is it then tunnels through a barrier into the upper laser level of the next period. As we discussed that from the lower level of the previous periodic to the upper level of the next period. So in a neighboring quantum well, in this it will work. The transition then relax on the ground, then it transfer to the another periodic level. So because this sequence is repeated in the every period, a single electron can generate one photon in each active region it transfers. So multiple photons we will get using several lengths and even about 100 such periods in the series, that will be the cascade. Therefore, yields high optical gain and multiple photons per injected electrons at the expense of the comparatively high required electric voltage. Operation order of the 10 volt are common, whereas only a few volts are sufficient for ordinary laser diode. So now we will discuss further in the next lecture. Thank you very much.